Hello learners, welcome in the video program of Physics at National Institute of Open Schooling Noida. On the behalf of National Institute of Open Schooling Noida, I Dr. Alok Kumar Gupta, Academic Officer Physics, welcomes you in the video program. Today our program is based on the topic electrostatics and its applications. Learners, have you ever noticed when you wear off your woolen clothes in winter season, there are sparkling with sound. This phenomena is related to electrostatic. This is very interesting to know, and this happens in our day-to-day life. For this topic, today our expert is Sri Sher Singh, Navagiri School, Lodi Road, Delhi. So, I welcome Dr. Singh sir, please.
Thank you, Dr. Alok. Really this topic is very interesting and you have given this example which is very much related to everyone, and let me tell you first what is electrostatics. Electrostatics deals with the interaction of electric charges at rest. A body is said to be charged if it has gained or lost electrons.
Sir, how electric charge can be produced?
Electrons are negatively charged particle with mass 9.1 into 10 raised to the power minus 31 kilogram and charge 1.6 into 10 raised to the power minus 19 coulomb. Coulomb is the SI unit of electric charge. If you want to produce electric charge, there are certain methods, and one very simple method is friction. So, the charge produced by friction is also called frictional electricity. Another method is by induction. The charge produced by induction is called induced electricity, and one more method is conduction. The charge produced by conduction is called current electricity, and very modern method is photoelectric effect. The charge produced by photoelectric effect is called photoelectricity, and charge can also be produced by heating. The charge produced by heating is called thermoelectricity. So, these are the certain ways to produce the charge.
Can you elaborate some properties of electric charge?
Definitely. One interesting property of electric charge is it is quantized. Quantized means the electric charge on a body is found in the form of integral multiple of elementary charge, that is the charge of an electron. If you want to write it in mathematics, Q is equal to Ne, where N is an integer and E is 1.6 into 10 raised to the power minus 19 coulomb. It is conserved. Charge can neither be produced nor be destroyed. It can be transferred from one body to another body in the form of electrons, and this method of transferring electrons from one body to another or from one place to another is called production of electricity or electric charge. It is also additive. The charge on a body is the algebraic sum of all the charges present in the body, and it is independent of mass and velocity. The charge cannot exist without mass, but it is independent of mass. Also, it does not depend upon the velocity as mass depends.
Can we have some activity to understand about behavior of charge?
We can understand the behavior of charge. Now, I have taken insulated stand in the form of this plastic bottle, which is easily available to all the learners in the surroundings, and this is the straw. When with the dry hand I rub this straw and I am gently putting it here, you can see the behavior of this straw. Now, it is suspended here. I am taking another straw by rubbing it same way, and now I am bringing it to the near to the straw. You can see that this straw is going away from it. You can see that this straw is going away from it. So, why it is moving away? Because both the straw are charged by rubbing or by friction in same way, and when two charged bodies of same charge are brought near together, they repel each other. So, you can conclude by this small activity that like charges repel each other. That is why this straw was moving away from it. Similarly, if the object after rubbing is brought near to the object by which it is rubbing, it will attract. You can see this activity again with the help of a cloth, and you can bring the cloth near to it and then it will be attracted. So, unlike charges attract each other. If you are putting a charged body on a wall or somewhere on a insulated things, it will stick to it. That is called induced electricity. What happens in induced electricity? When a charged body is brought near to uncharged body, the charge inside uncharged body is redistributed, and unlike charge comes towards the charged body, and that is why there is the force of attraction, and induction is always deals or start by attraction force. So, these are simple activities which you can understand with the help of activities. How much force between the charges the force between two charges can be calculated by Coulomb's law, and this law states that the force between two charges is directly proportional to the product of the magnitude of the charges and inversely proportional to the square of the distance between them. If we write charges by q1 and q2, you can write F is directly proportional to q1 q2, inversely proportional to r square, and the force will become 1 upon 4 pi epsilon naught q1 q2 upon r square, where 1 upon 4 pi epsilon naught is electrostatic constant. If you want to write it in vector form, you can write the unit vector r cap along the direction of r, and then you can write vector r divided by its magnitude. So, the force becomes 1 upon 4 pi epsilon naught q1 q2 vector r divided by vector r modulus and its cube, where 1 upon 4 pi epsilon naught has mathematical value as 9 into 10 raised to the power 9 Newton meter square per Coulomb square, and epsilon naught is electric permittivity of free space. And one thing is very important here, that is the electric permittivity of any medium can be written as epsilon naught into epsilon r. Here epsilon r is relative permittivity or dielectric constant. For free space, air or vacuum, epsilon naught is equal to epsilon and epsilon r is equal to 1. So, the electric force is a very strong force. If two charges each of magnitude of 1 Coulomb each are placed at a distance of 1 meter apart, you can calculate force between them, which comes equal to 9 into 10 raised to the power 9 Newton. It is that much strong that it can hold a mass of 900 billion kilogram. So, electrostatic force out of all the 4 type of forces in nature is a very strong force, and the intensity of this force can be calculated in terms of electric field intensity. Electric field intensity is the force experienced by unit positive charge in electric field. If a test charge q naught is placed in the electric field of charge capital Q at distance r, then the force experienced by test charge q naught will be 1 upon 4 pi epsilon naught q into q naught upon square of r, and the force experienced by unit positive charge means 1 Coulomb positive charge, the electric field intensity becomes 1 upon 4 pi epsilon naught q upon r square, where q is that charge which is producing electric field, and you can also write it in vector form. Its SI unit is Newton per Coulomb. It is a vector quantity and its direction is along the force experienced by test charge.
Sir, how can we map the electric charge?
You mean the electric field produced by electric charge?
Yes.
Yes, it can be mapped in terms of electric field lines.
Okay.
And electric field lines are the imaginary path followed by test charge in electric field. Electric field lines originate from positive charge and terminate into negative charge. The tangent drawn at any point on electric line gives the direction of electric field at that point. They do not intersect each other because two directions of electric field are not possible at a point, and concentration of field lines is more in strong and less in weak electric field. Number of field lines is directly proportional to the quantity of charge. If you are taking two charges q1 q2, then the ratio of the number of field lines n1 upon n2 will be q1 upon q2. They do not exist in metals. They originate or terminate normal to the surface. They are parallel and equidistant in uniform electric field. To have more idea about the electric field lines, you can see the different types of field patterns here. These field patterns are shown for q is equal to greater than 0, and here we have taken the pair of charges q1 q2 in which q1 and q2 both are equal but positive, and in this case q1 is greater than q2 but q1 and q2 are positive. Here you can see that symmetry of the field lines. Field lines are extended up to a larger distance from q1 because q1 has larger magnitude. In this field patterns you can see that field lines are terminating and coming out normal to the metal plate placed here. If you place a metal sphere in uniform electric field lines, again the field lines appears to come out from the center of the sphere, and in metallic sphere there is no field line. It means the electric field inside the metal is 0.
Can we understand field lines in terms of electric flux?
Electric flux is the number of field lines passing through a surface held normal to the direction of electric field. Mathematically you can say that electric flux is the dot product of electric field and surface area, that is Es cos theta, and here very important is the theta. Theta is the angle between electric field and normal drawn to the surface. One thing is very important here, if E is not equal to 0, ds is not equal to 0, but theta is that quantity which can make the flux 0 because if surface is held normal to it. And second important point is this, when we draw the normal to the surface, we have to draw this normal outward. Let us try to understand this theta with the help of this diagram. In this diagram, electric field lines are representing electric field intensity and two surfaces are held. One surface has normal in the direction of field, so theta is 0 and the flux is maximum. The same surface is tilted by angle theta, so normal makes an angle theta with the direction of field, so it is not equal to 0, it is little more than 0, and when theta is greater than 0, cos theta will be less than 1 and the flux will be less than its maximum value. That is why phi 2, the flux of the second surface, is less than the flux of first surface. Here we can understand it with a very small activity. If we are taking this as a surface and these are the electric field lines here, if we are taking this imaginary surface through which we are counting the electric field lines in terms of flux, so you can see that all the field lines are coming out from the surface, and when we are drawing the normal to the surface, it is in the direction of field. So the maximum flux is linked with the surface. So this is E into S. If I am removing the surface, now I have replaced this surface at an angle theta. So now you can see the electric field lines which were coming out earlier is decreased. Now these field lines which you can see is out from the surface. It means electric flux is reduced. And in terms of mathematics, if you are drawing the normal on the surface, this angle in the direction of field here is not equal to 0, it is little more than 0. So cos theta will be little less than 1 and maximum electric flux, which earlier was equal to the electric field intensity multiplied by the surface area, will be lesser. So electric flux is very important, and in terms of electric flux you can see it is calculated mathematically with the help of a Gauss law, which states that the electric flux emerging out from any imaginary closed surface is always equal to 1 upon epsilon times the charge enclosed within the surface, that is phi is equal to q upon epsilon. If it is a free space, then it will be q upon epsilon naught. For elementary surface, we can write it as integral of E ds cos theta, which is equal to q upon epsilon naught. Again, theta is the angle between electric field and normal drawn to the surface.
Sir, can you elaborate some important applications regarding Gauss law?
Yes, Gauss law is very important, and with the help of Gauss law, you can calculate electric field intensity of a point charge. Here there is a point charge and dotted surface, you may call it Gaussian surface. It is enclosing the charge q. If radius of this Gaussian surface is r and normal is outward, we can apply the Gauss law, that is integral of E ds cos theta is q upon epsilon naught, and ultimately the surface area of this Gaussian surface is 4 pi r square. So E becomes 1 upon 4 pi epsilon naught q upon r square. It is the same result as we have discussed earlier. And another thing, if charge is linear charge, so electric field intensity can be calculated by putting a cylindrical Gaussian surface here to enclose the linear charge of linear charge density lambda, and here you can see there are three surfaces. One is first circular face, second is curved face, and third is again a circular face, and you can draw the direction of electric field on these surfaces and the direction of normal. So here you can find that the circular face 1 and circular face 3, the angle between normal and electric field is 90 degree. They do not have any contribution in electric field intensity, it is only due to a curved surface. Here you can apply the Gauss law, integration of E ds cos theta is q upon epsilon naught. Here E ds cos theta can be written for all the three surfaces, that is 1, 2 and 3, and in place of q we can write linear charge density lambda multiplied by L, and you can simplify it. The curved surface area is 2 pi r L and circular face have integration equal to 0. So electric field intensity is lambda upon 2 pi epsilon naught r square, and here it is not r square, it is r. Another important application is electric field into a plane sheet of charge. Here we have considered a plane sheet of charge and a cylindrical surface passing through it enclosing the area A. So we can apply here Gauss law for area A, which can involve the charge equal to surface charge density multiplied by area. Again you can draw three surfaces, that is one circular face 1 and curved surface 2 and circular face 3. But in this case it is very interesting that at circular faces normal and electric field is in same direction, but at curved surface theta is 90 degree. So now here you can apply the Gauss law. Integration of EDS cos theta is equal to again q upon epsilon naught, and again EDS cos theta can be written for 3 surfaces separately, for 1, 2 and 3, which is equal to sigma A, which is equal to charge divided by epsilon naught, and 2 circular faces gives integration as E into A, and curved surface gives 0. So it becomes sigma A upon epsilon naught, and electric field intensity is equal to sigma upon 2 epsilon naught. One very important phenomena in electrostatic is electrostatic shielding. When a charge is placed in a metallic case or it is enclosed by a metallic surface, the whole charge appears at the surface as depicted in the diagram. So if we apply Gauss theorem here, EDS cos theta, the charge enclosed is 0, so electric field becomes 0. The region inside the metallic case becomes free from electric field. This phenomena of vanishing the electric field from a region is called electrostatic shielding.
Sir, can you explain some practical application regarding electrostatic shielding in day-to-day life?
Definitely, electrostatic shielding is very important phenomena. Any electrically sensitive instrument can be placed in a metallic case to protect it from the effect of electric field. Secondly, you will be wonder, there is a very natural phenomena. During the lightning, you would like to remain in a house or in a car. Definitely in a car, because car is a metallic case. So you are safe inside the car, not inside the house, because in lightning very large quantity of charge pass from clouds to the earth. If it pass through a body, and body will be diminished at the moment. So to save ourselves, we will like to remain inside the car. This is another electrostatic shielding phenomena. Or if you want to make any region free from electric field, you can put a metallic case on it. That is why electrostatic shielding is very much related to our day-to-day life. So these are some important properties of electric charge, flux, field, and all these are the natural phenomena which affect our environment, which affect our day-to-day activities, but we have to take huge an advantage of all this strong force, that is the electrostatic force between the charges.
Thank you, sir. Dear learner, in this lecture you have read about electrostatics and its application, and I think you have noticed there are so many practical phenomena related to natural phenomena and day-to-day life our sir has been discussed, like what is electric flux, electrical shielding, and also we have discussed about electric charges, that like charges repel each other and unlike charges attract each other. Thank you, sir, you came in our studio. I think our learner after seeing this program will be more benefited and will be more clear about this subject. Thank you, sir. Once again,
no need to mention, it is my privilege. Thank you.